So we now need to see how the algorithms are evaluated, because before we see how the algorithms work, we require to see how the algorithms are evaluated. There are two types of supervised learning algorithms, as I said: classification and regression. So for both classification and regression, we have different metrics. Let's see them. As supervised learning algorithms are of two types, in the same way, the outcomes are also of two types. One type I already have stated, it is classification, of which the outcomes can be categorical. Second can be numerical. Well, among categorical, we can have binary outcomes or multi-class outcomes. Among numeric, we can have continuous outcomes or discrete outcomes, like counts. First, we are going to see how we evaluate the categorical outcomes. Imagine that we have got a classification problem which is a binary type, and we have got some 12 observations in the test set. And y_test lists down the existing observations outcomes of the test set. Ypred is a result of the predicted values. Such kind of predicted values may be from the functions like predict and not from the functions like predict_proba. So as far as the first observation is concerned, we can read in the following way that the y_test value for the first one is 0, means actually it is 0, and it has also been predicted as 0, so it has been correctly predicted. Second observation is actually 1, and it has been predicted also as 1. That's not the case with observations like 5 or 7 or 8 or something like that. For example, observation number 5, we see one thing that it was actually 0, but it has been predicted by our algorithm as 1. Similar is the case with observations 8th and 10th. And story with observations 7th and 11th is completely opposite. In this case, y_test is 1 and the prediction is 0. The following table, which is at the right, will be a summarization of the outcomes which we have got. Now, this is nothing but a pivot table like table which we generate in Microsoft Excel. Well, here we are going to write count of all those observations for which y_test was 0 and predicted was also 0. If we count them all, it will be 1, 2, 3, and 4. 1, 2, 3, and 4. So we should be writing 4 over here. 4. Let's talk about the cases with which we had actually 0, means y_test was 0, but the predicted was 1. So such kind of observations we see 1, 2, and 3 cases are there. Hence we will be writing 3 over here. Now here should be the count of all those observations which were actually 1 but were predicted as 0. In that case, it will be 1 and 2. And here will be that particular count where it was actually also 1 and predicted also 1. We can count them 1, 2, 3. Well, 1, 2, and 3. We see these 3 observations over here. Hence, this particular matrix which summarizes the findings, actually mean for comparison of predicted with the actual, is called classification confusion matrix. We can now have the margin totals of these. So it will be 7, 5, 12, and obviously 6 and 6. Hence this completes our classification confusion matrix. Now, if we would have had more than 2 outcomes, then our confusion matrix could have been of that dimension. For example, if we would have had some 4 outcomes, okay, so in that case our confusion matrix size will be 4 by 4. We are having over here in this case binary classification, hence the classification matrix size is 2 by 2. Hence we see one thing for sure, that there are possibilities in different predictions. One possibility is that we won't be getting error at all. So we expected a 0, but we got 0. We expected 1 and also we got 1. But in the second 2 cases I can say, we expected 0, but we got 1, and we expected 1 and we got 0. Okay. So this is the way we summarize the results. The values which we have tabulated are called by a certain name. Usually, what happens is 0 is many times treated as a negative class and 1 is many times treated as a positive class. So 0 means negative and 1 means positive, henceforth we will be calling. So if any value is actually negative, actually 0, and it is predicted also to be 0, it will be called as true negative. The value which is actually positive and also has been predicted as positive can be called as true positive. The value which is actually negative but has been predicted as 1. So you see, this has been predicted as positive but actually was negative. Hence, it is called as false positive. Now, what about this value? It has been predicted as negative. In reality, it was positive. So it is false negative. So coming again, true positive is what? Correctly assigned observations to the positive class can be called as true positive. True negative are correctly assigned observations to the negative class. True false positive, wrongly assigned observations to the positive class. False negative is wrongly assigned observations to the negative class. So hence we saw the things in the confusion matrix, which is used for classification models. In the next video, we will see how the different metrics like precision, recall, F1 score and accuracy are calculated. Thank you. Hello, welcome back. In the previous video, you saw how the confusion matrix counts are created based on the classification problem. In this video, you are going to see what metrics are calculated based on the counts given in the confusion matrix. Let's see them one by one. Now, let us see how to calculate some classification metrics like accuracy score, precision, recall, F1 score, area under the curve, and log loss. Now, we already have seen how this classification confusion matrix is tabulated. Let us see now how the accuracy is calculated based on the classification confusion matrix. It is number of correct decisions divided by total number of decisions. That is true positive plus true negative divided by the entire set of observations. For our problem, the accuracy score can be calculated as 4 plus 3. This being true positive, true negative, sorry, true positive, well, true positive plus true negative divided by all the observations, that is actually 12. Hence, for our problem, 7 by 12 is the accuracy score. Now, let us see how confusion matrix can be displayed with the help of Python code. There is a function called confusion underscore matrix with which the confusion matrix can be displayed. For the latest version of scikit-learn, we have got one function called from predictions, which can be called on confusion matrix display object, with which we can see heat map of our confusion matrix. Also, we can extract the true positives, negatives, false positives, negatives from the confusion matrix with the help of the function ravel. Let us consider now this case in which we are already having a confusion matrix created and also accuracy score evaluated. Some softwares or some libraries mention misclassification error in place of accuracy. It is nothing but 1 minus accuracy. Apart from accuracy, we see some few more metrics which have been calculated over here. Let's see them one by one. Let's talk about precision. Now, what is precision? The precision over here, as you will see, it has been calculated as the true negatives divided by the total number of predicted negatives. Means, in the sense that among all the predicted negatives, how many of them were really negative? Okay, so among predicted negatives, let me tell you, 1, 2, 3, 4, 5, and 6. Among these 6 negatives, the actually correct negatives were 1, well, 2, 3, and 4. Okay, so hence our precision for 0 will be 4 upon 6. Similarly, precision for 1 means among the predicted ones, 1, 2, 3, 4, 5, 6. Among the predicted ones, how many of them were really ones? Means how many of them were really positives? So it was this one, it was this one, and it was this one. As you see, it was among 6, there were 3 which came up to be really positive. Okay, hence the precision for 1 can be 3 upon 6. Let's talk about recall. Among all the actually existing zeros, okay, So how many zeros were there actually in the test set? 1, 2, 3, 4, 5, 6, and 7. 7 zeros. Among the 7 zeros, how many were predicted by the model as really zeros? So there were 4 in all. Hence, recall for 0 will be 4 by 7. Similarly, you will find recall for 1 will be 3 upon 5. Let me tell you now why we intend to have precision and recall calculated. Hence, what precision tells is the proportion of correct predictions among each predicted categories. And recall tells the proportion of correct predictions among each existing categories. We have a third measure related to precision and recall, and that is harmonic mean of precision and recall, which is called F1 score. The best value of F1 score is 1 and worst value of F1 score is 0. Same is the thing with precision and recall. Many times, instead of accuracy score, F1 score is preferred as the model evaluation metric. You will also notice that the output calculates precision, recall, F1 score for every category, as well as it also calculates average. Average means macro average for all the categories, also weighted average. Weighted average weights are taken with proportion to the actually existing prevalence in the test set. Now let us see how each of these is calculated with our Python functions, scikit-learn. There is a function called accuracy score, with which we pass the existing NumPy array or a panda series and the predicted panda series or a NumPy array, with which we get the accuracy score. And there is a function called classification report, which calculates all the things which we discussed. Also, you will see that confusion matrix is one measure, and related to the confusion matrix is the classification report. Many times we display both the things in order to see the goodness of it. Also, you will notice one more thing in classification report, that we also get accuracy score. Hence, we saw accuracy, precision, recall, and F1 score. In the next video, we will see how we compare the predicted probabilities with the existing values. Thank you. Welcome back. In the previous videos, we saw categorical comparisons using accuracy score, using precision, recall, and F1 score. But problem is that many of or all of our machine learning algorithms, when they predict, classification algorithms give probabilities as the predictions. Now, with these probabilities, the categories are generated based on the thresholds. Well, comparing with a specific threshold can be done with, no doubt, with F1 score, accuracy, precision, and recall. But we require to see comparatively that how to evaluate the quality of probabilities which the classification algorithms give us. Let's first of all see how the quality of probability matters for a certain prediction. Before we go to the next topic of ROC curve, I want to mention here that this recall for 0 and recall for 1 has got two names. Recall for 0 can be termed as specificity, and recall for 1 can be termed as sensitivity. You require to know both these terms also, because at times these terms, specificity and sensitivity respectively, are used in place of recall for 0 and recall for 1 also. Apart from the names like specificity and sensitivity, they are also called as true negative rate, TNR, and this is called true positive rate. You require to know all these terms because some software mention not of recall but of sensitivity, specificity, or some mention true positive rate or true negative rate. Hence, let us understand what is ROC curve. ROC curve, let me tell you, is basically plotted for only binary classification algorithm. Now, it is plotted with sensitivity or true positive rate as the y-axis and 1 minus specificity. 1 minus specificity means 1 minus true negative rate. It will be false positive rate. Okay. And this sensitivity and specificity are calculated at different thresholds. Let me clarify what is that. Now, consider that you have got over here the predicted probabilities. You see, all of our classification algorithms as the predicted outcomes give us probabilities by default. They don't give us the direct values of ones and zeros. So over here we consider that one model is there which has got probability of occurrence of 1. Okay, see, this is probability of occurrence of 1 which this model has given. It is 0.6. Probability of occurrence of 1 is 0.4. Naturally, if probability of occurrence of 1 is 0.6, then probability of occurrence of 0 will be 0.4. Probability of occurrence of 0 for this particular case will be, needless to say, 0.6. For this case it will be 0.2. Likewise, we list down first of all probabilities for 1 only. Okay, say suppose that we have got two different models, model 1 and model 2. Now model 1 predicts the first probability for the first observation as 0.6 for 1, and model 2 predicts it as 0.7. Considering, you see, the thresholds, you see what happens is our ones and zero series is generated with a threshold 0.5. Means what? 0.5 in the sense that if this probability is bigger than 0.5, it is more probable that it is 1. This probability is less than 0.5, it is more probable that it is 0. So over here, I'm writing one Excel function for doing that. Hence is our output. Similarly, we can have for the second model the threshold as 0.5. Considering both these, we see definitely one thing, that the outcomes of ones and zeros with the threshold 0.5 are coming out to be same. Now if you consider these as predictions and these as a test set and construct a confusion matrix, whatever confusion matrix you will be having, okay, you will be having same confusion matrix with y2 with y test. Okay, because the figures of 1, 1, 0, 0, the predictions match with these two. But you will see at the probability level, they don't match. Basically, I can say one thing for sure, that among these two, the quality of probability of the second model seems to be better because this second model is closer to 1. As far as this two probability comparisons are concerned, we see one thing, that this 0.45 and 0.4, both of them are wrong because both of them are less than 0.5. Hence, among these two, we can see that 0.45 seems to be better. Likewise, we can have consideration of all the probabilities, with which we clearly see that the quality of probabilities of from model 2 seems to be better than that of model 1. But if we consider confusion matrix, then all the metrics of confusion matrix will come out to be same, which will be deceitful. Hence, we require a metric which evaluates the model based on probabilities. Basically, what happens with predictions through classification models is that the models give predicted probabilities. Now we had these two models with different probabilities, though still with the help of threshold of 0.5, we saw that the final outcomes were same. Now this will not be a good thing in the future when we choose some specific parameters for tuning any machine learning model. Hence, we require to evaluate a model not just based on ones or zeros, but on the basis of the quality of probabilities. ROC AUC, that is area under the curve for ROC, and log loss can help to serve this purpose. Let's see that in the next video. Thank you. Welcome back. Before we understand area under the curve, we need to understand how the
Outcomes can be calculated with the help of different thresholds. Let's see them first.
Now, let us think of evaluating our confusion matrix with different thresholds. For example, keeping 0.1 as the threshold, if we consider 0.1 as the threshold, and if means every probability, if it is bigger than 0.1 then 1, otherwise 0. Likewise, we will be having different set of ones and zeros. Well, maybe let us try out some other threshold like 0.25. You see, when the threshold changes, the series of ones and zero will change. Now what happens is, with different thresholds, like now I am trying over here, hence for different thresholds we get different series, and for every series we can compare this series with the y-test and have a confusion matrix. With the confusion matrix we can calculate recall 0 and recall 1, that is sensitivity as well as specificity. Okay, so hence you see, for each one of these thresholds we calculate sensitivity as well as specificity. Now for our curve we will be requiring the different values of sensitivity and specificity for different confusion matrices at different thresholds. Hence, considering this, we have a area under the curve. We have a curve and we calculate area under the curve. Okay, with 1 minus specificity as the x-axis and sensitivity as the y-axis. In ideal case, when the outcomes are perfect, then area under the curve will be 1. The area under the curve's worst value will be 0, and any value which will be bigger than 0.5 will be better value. Okay, but as far as the goodness of fit is concerned, many people consider area under the curve greater than 0.8 as a very good value. Area under the curve like 0.6 and 0.7 will not be very good, but it will be okay. ROC can be generated with the help of the following functions in Python scikit-learn. We see that there are two functions, ROC underscore curve and ROC underscore AUC underscore score, which is mean for calculating area under the curve. ROC underscore curve generates basically the 1 minus specificity and sensitivity and threshold, these three vectors, or I can say these three numpy arrays it generates as the output, and these three can be passed on to our matplotlib function to display the ROC curve. Apart from ROC curve, we also calculate log loss. Log loss is calculated by the following formula. Log loss for a particular value with the probability will be value, or 1 or 0, multiplied by logarithm of the probability plus 1 minus that value into logarithm of 1 minus probability. We take average for all the terms, and usually always what happens is logarithm of a probability will always be negative. Okay, so hence this term, if it is not negated, it will be by default negative. Hence we will see in many textbooks that we have a minus 1 multiplied to this particular formula, in the sense that we want to show it as a positive figure. Well, whether we show it as a positive figure or we show it as a negative figure, more important is the closer that figure is to 0, better is the model.
having learned all the evaluation metrics related to classification, starting from accuracy score up to the entropy or log loss, if question is there in your mind, which one to use for optimization, which one should be preferred more? Well, many recommend log loss as the best one for optimization. Well, what happens is that when we are presenting the results to the people who may be end users of our algorithm, then many times log loss or area under the curve won't be that simple to explain as will be accuracy score, precision, and recall will be. Well, definitely one thing is that if we take care of log loss or we optimize our parameters, we fit our model in such a way that log loss remains low or whatever, area under the curve remains as big as possible, then automatically what is going to happen is that our precision, our recall, our F1 score, our accuracy score definitely are going to improve. Hence, for optimization, I can say that prefer log loss or area under the curve, and for presenting the results as an accuracy or as a precision or a recall will be simpler for you. Thank you. In the earlier videos, we saw how the classification models are evaluated. Now, we will see how regression models are evaluated.
Well, when the response is numerical, then we cannot have confusion matrix. We will require the other metrics like mean absolute error, mean squared error, and R square. The least is not all inclusive. There are other metrics also like mean absolute percentage error or root mean square logarithmic error, etc. Mean absolute error. Mean absolute error can be calculated as error means what? Error means the difference between the predicted value, you see, and the observed value. We absolute the difference between them. We call it absolute error. And then we have an arithmetic mean of it. In Python, we have a function for that called mean underscore absolute underscore error. Similarly, another metric which is commonly used is mean squared error. Mean squared error is you calculate the errors, you square those errors, and you take arithmetic mean of them. That is called mean squared error. The mean squared error can be calculated with the help of scikit-learn function with mean underscore squared underscore error. Common thing in these two, that is mean absolute error and mean squared error, is that lesser these values are, better will be the model prediction. Third one can be R square score, or also known as coefficient of determination in some of the outputs. Coefficient of determination or R square is 1 minus, you see, 1 minus, let's understand this term. It is error and square of it. So sums of squares of the errors divided by, what is this? This is yi minus y bar. It is arithmetic mean. So this is basically deviation from mean. So we take deviation from mean, square them up, okay, then take a sum of it, okay, divide it by this squared errors, sums of squares of errors, 1 minus of it. Well, one thing what we can observe is, in ideal scenario, when yi and yi cap will be same, then in that case the numerator of this term will be 0. Hence, the best value of R square score will be 1. It will be 1. Okay. And worst value of the R square score can be anything. Okay. This R square which we are calculating is based on the yi cap that are predicted values. The R square score can be calculated in our from our scikit-learn function R2 underscore score. Let us see one illustration of it. Say for instance that we are having a y-test as the existing set of figures, and some model predicted these figures and another model predicted these figures. And now we want to compare goodness of fit, or we want to compare the models. Hence, when the first model I am comparing, first of all I have calculated the absolute error over here. So I have absoluted these errors, and then I have averaged these errors, then squared error, and then the R square score. You will see with the comparison of two models, one thing that R square score for the first model seems to be bigger. It is closer to 1. Also, you will observe one more thing, that the mean squared errors for the first model seem to be lesser than the second model. First model seem to be lesser than the second model. Hence, first model seems to be better as far as the predictions are concerned.
Hence, we saw the evaluation of regression models. Well, we saw welcome back. In this video, we are going to see how cross-validation works. In all, we are going to see two types of cross-validations. One is trend test split and another one is k-fold cross-validation. Well, trend test split or k-fold cross-validation, whatever are the two, are done with supervised learning. Hence, when we require to have always in supervised learning, as I said, a response variable or outcome variable and the other variables which affect that outcome variable. Maybe one outcome variable might not be there, maybe multiple outcome variables, but we will deal with multiple outcome variables later. Let's deal with just one outcome variable.
Consider that we have, for a supervised learning algorithm, we want to split the data. Well, the data is splitted into two or more partitions with trend test split method. So first partition will be a major partition, second partition will be a minor partition, and also sometimes another minor partition may also be there. Now, what is the intention, let me tell you, behind this minor partition? Consider that we are having just two partitions, training and testing. Well, with training, we will be building the models on the training set, and with testing or validation partition, we will be evaluating the models on the testing or validation partitions. Let's see the workflow of it. So here, suppose that we have got some 1000 observations. We intend to partition those 1000 observations. Okay, we intend to partition those 1000 observations, as I said. We have 1000 ones. And we plan to partition them with some proportion, 70%, 30%. As I have already said, that the major partition will be training partition, minor partition will be testing partition. On the training partition, we will be building model. Now you will wonder about one thing: why aren't we building model on the entire data, and why are we leaving the 30% data unused? Let me tell you, it is not unused. It is for assessment of the model. This testing proportion, the fraction of testing may be 20% also, maybe 10% also. So in some problems we do have 80-20, 90-10, 95-5, etc. Purpose in having this testing partition is that we intend to test our model which we are building on some unseen data. Because the model building, if we do on the training data, then on the training data, well, if it is tested on the training data, not a surprise that it will perform very well on the training data. Question arises whether this particular model will perform on the unseen data. What do I mean by unseen data? Let me tell you. The data which hasn't been used to train the model can be called as unseen data. Okay, so over here our testing data set is the unseen data set. Now, after we build the model, we are going to consider only that part of the testing data which is without response variable. Let me tell you one thing for sure, that this entire data is containing x1, x2, x3, xp, and also y. Needless to say that this also contains x1, x2, x3, xp, and y, and this also contains x1, x2, x3, xp, and y. Now, what I'm trying to tell over here is we will be considering this time testing data without response, means testing data x1, x2, x3, xp without y. I'm talking about that. So on such kind of data set, what we'll be doing is we'll be applying the model which has been built on the training data set. Now, what I mean by model building, let me tell you in short. Whatever are our x values, maybe x1, x2, x3, xp values, and y, we try to establish a strong link between the two. That is model building. We will see different approaches of establishing this strong link between x variables and y variable later on. But before that, let us try to understand this workflow. Once we have built that strong link, whatever, well, then we'll be applying that link on the unseen data, on that particular data on which the model has not been trained. And afterwards, we will be having a response, and with that response, we'll be comparing it with the existing Y to evaluate the goodness of it. Let me also tell you over here that we will be using several approaches. Say M1, M2, M3. Say we are using some 10 approaches. For all these 10 approaches, we will be having evaluation 1, evaluation 2, up to evaluation 10. For that evaluation for which that particular model is the best, say suppose for the second evaluation, we see that the model is, this second evaluation is the closest one as far as existing values and predicted values are concerned. In that case, model 2, which is corresponding to the evaluation 2, will be called as the best model. This is the way how we choose the best model with this trend test split.
We saw how algorithm is evaluated with trend test split method, whether it may be classification or whether it may be regression. But the trend test split mechanism or trend test split method has some drawbacks. Hence, we more trust on the results related to k-fold cross-validation. But for quickly testing any machine learning model, it will be very simpler for us to test it using trend test split. Thank you.
In the previous video, we saw trend test split. Trend test split has many drawbacks. Now, with k-fold cross-validation, we divide the data into k equal parts and predict k times and evaluate k times and take average of it. Let us see that how we do. Well, before we see k-fold cross-validation, we should first see what is really the problem with two partition split. So in two partition split, we have trend test split with model building on the trend set, model evaluation on the test set. Now, say that we are having some 10 observations in the entire data set. Now, if these 10 observations with the trend test split have been splitted randomly, say suppose that we have 6, 5, 8, 10, 1, 3, 1, 2, 3, 4, 5, 6, and one more. Let's consider this observation. Now, if among the 10 observations, 6th, 5th, 8th, 10th, 1st, 3rd, and 2nd are in the trend set, then obviously remaining will be in the test set. So those observations will be 9th, 4th, and 7th. Now we may consider building the model on all these observations, and we'll be assessing the model on these observations. Now say suppose that for first model, that is M1, we have the evaluation. For M2 also we have evaluation. Likewise, we have evaluation for some 10 models. For every model, what we observe in this case is these observations 9th, 4th, and 7th don't get a chance to get participated in the training set. Okay. Why? Because they have been assigned the task of assessing. If it may happen that if 9th, 4th, and 7th contain some important patterns for model building, then we will miss them out. Hence, this particular trend test split is handicapped with such kind of thing where every observation from the data doesn't get a chance to participate in the model building, as well as every observation doesn't get a chance to get evaluated in the testing data set. As against that, just let's look at how the k-fold cross-validation works. K-fold cross-validation doesn't rely on just 2 or 3 partitions. It splits the data into k equal partitions. K may be 5, k may be 10, k may be 20 also. So given the data we have some equal k partitions. And let us see what we do with these k partitions. Say suppose for our problem, k is equal to 5. So hence we have got the 5 equal partitions A, B, C, and D respectively. Let us consider that we have some 100 observations, and if these 100 observations are partitioned into 5 equal parts, obviously every partition will be having 20 observations. Now we consider in this case A as the test set and B, C, D, E combined as the trend set. So obviously what is going to happen is we will be having 20 observations in the test set and 80 observations in the trend set. Well, considering this, we do model building on the trend set and predict on the test set. We do model building on the trend set and predict on the test set. So ultimately, say that we have a metric considered as area under the curve. So for this fold combination with set A or fold A being test set and all others being trend set, let us say that we have one particular metric calculated. With building this and assessing with this, we have some area under the curve calculated. Now this will be stored firstly as first metric for the first fold combination. For the second fold combination, we consider B as the test set and A, C, D, E as the trend set, and building on this A, C, D, E, which will be altogether a data set of 80 observations, and data set B with 20 observations. We'll be having another evaluation metric. Well, again, another, I will say, value of evaluation metric called A2 maybe. Let's denote this by A2. These will be actually the values. Okay, so it may be 0.83, 0.87 kind of values will be there. Likewise, C as a test set and A, B, D, E, then D as the test set. Likewise, we have all other fold combinations evaluated. Having this evaluated, we can now calculate the mean of all this, mean of all the metric values. This will be the metric for k-fold cross-validation. Hence, we will be trying out different models or different model parameters with same k-fold combination. Now, in this particular method, what we see is every observation in every fold gets equal chance to participate in the trend set as well as test set. Hence, the average of the metric value will be more trustable than the trend test split metric. Hence, we saw k-fold cross-validation technique. The k-fold cross-validation technique results are more reliable than trend test split results. Hence, we will see in all the other options related to tuning that the functions like grid search CV or functions like randomized search use k-fold cross-validation technique.